So, welcome everyone. First up, I want to just ask real quick, check in on how the project is going. You all said that some of you were trying to say you only needed a few days. So, how many people are done with it so far? Okay, pretty low numbers. Yeah, so make sure you get this done. I'm not going to extend it again. It doesn't make sense to. In fact, I'm probably going to release a new project on Wednesday. Just for the record, it should be easier than this one in terms of like the coding and the nitty-gritty aspect of it. In terms of the algorithm side, it might be slightly more complicated for some people. Depends how good you are at dynamic programming. It will, in fact, be a dynamic programming problem. Cool. Any questions? Cool. By the way, I'll just share. I had the team that I've been coaching for the AA Olympiad went and took round 2, and they did great. So good job on them. Yeah. Some of them actually, I gave a link to the YouTube, so they might actually see that. Anyway, one thing that I was somewhat inspired by going there, they took a very hard test on machine learning, and machine learning is something that a lot of kids, as some of you know, I teach and I created 3D9 at UMass. A lot of kids go in underprepared, and in particular, there is one specific part that a lot of students have trouble with. They have trouble with backpropagation. Backpropagation is an algorithm that is very important in machine learning. We'll discuss a little bit of why it's important, but that's not a place for this class to go in deep there. But it is an important algorithm. We're going to learn today how it works. We're going to notice that it's dynamic programming, and hopefully we're going to get ahead in case any of you are interested in machine learning. If you're interested in machine learning, pay attention to this topic. This is also going to be good practice for dynamic programming for the rest of you, and it is obviously an important algorithm. This is one of the most important modern algorithms. So if you want to understand what sort of algorithms actually exist and are actually important, this is one of them. Okay? Cool. So, first things first, this is going to be related to calculus. And some of you may be internally grown at that, because we do have somewhat messy calculus education, I think, at UMass. Not that we don't have good calculus education, but it's just not very consistent. Some people walk out of it not knowing that much. So we're going to start with a couple of definitions and do a couple of examples before we get into the actual algorithm. So first up, first thing I want to point out is we can have a function like so. Let's say y equals x1, x2 plus x3, x4 divided by x5, let's say. Something like that. You know what? Actually, the whole thing multiplied by x5. That'll be easier. So something like this, all multiplied by x5. Now, this is a multivariate equation that is, if that term scares any of you, it means that there's multiple variables. Very easy. First definition is going to be a partial derivative, which I'm going to assume that people, if you haven't taken Calc 3, can infer from the definition I'm about to give. If I take the partial derivative of this function, that means that I am going to find the derivative with respect to just that element. So this is saying I'm taking the derivative with respect to only one of my variables rather than the only one, which is what a derivative generally would mean. Okay. Secondarily, and as an example here, the partial derivative of x5. Could someone tell me that? Yeah. Everything in the parentheses. So when we're doing this, we treat every other variable essentially as a constant. So we would just have that as the derivative here. Okay? Cool. Anyway, so that's partial derivatives, and I'll leave this here, and I'll leave this as an example, just so you guys have it. It's x1, x2, plus x3, x4. You just treat all of that like it is a variable. The other big definition is going to be a gradient. So the gradient of this function, with respect to here x, where x is going to be all of our terms, so it's just x1, x2, x3, x4, x5 is going to be our x vector. This is just a notation, a way to group them together. Again, hopefully everyone has no trouble with this. If you're having trouble with the notation, you can ask me to clarify. I'm willing to do that at this beginning part of the class, but it'd be better to get it sooner rather than later. And this gradient is going to be all of the partial derivatives with respect to our vector. And very easily, this is just going to be an array of all of the partial derivatives with the corresponding elements. So this would be the partial derivative of y with respect to x1, same order as our list what x is, partial derivative of y with respect to x2, etc., partial derivative of y with respect to x5. Okay? At this point, if you have a question, ask me. If we move on from here and you don't understand this, you're going to miss a lot of the class. Okay? This symbol down here, this is a 5, if that's what we're talking about. This is it's called a partial symbol. Here, I'll rewrite my 5 because I did draw it kind of weird. 5. Yeah. Okay? Cool? Cool. All right. So now, a little bit of the motivation. Why do we care about this? Does anyone know why we care about something like this? Yeah.
It's good for.
So one thing I could do hypothetically, so sort of yes, but we'll talk a little bit more about that. But one thing I could do hypothetically is if I wanted to find the minimum of this function, let's say. This one won't have a minimum because it's all positive. I'll just have large negative numbers here. But if I wanted to find the minimum of some function, let's say x1 minus x2 squared, something like that, then what I can do is I can find where the gradient is equal to 0. So I need to calculate the gradient first, then calculate where it's equal to 0, and then that would give me a minimum or a maximum or some sort of saddle point. Don't worry too much about the geometry and this part of it, but I just want to motivate it for the people who are interested. What we end up realizing is that if we want to optimize any function, we actually can use the gradient directly to do something called gradient descent, which if you're interested in the algorithm, you can look it up. My YouTube channel actually has all the 389 lectures, so if you'd like to see this in its context, you can see it there. Whatever the case, this is not the only reason we care about gradients. We care about gradients in lots of fields. We care about gradients in lots of situations. In particular, though, we are taking the gradients in the real world of neural networks, which are going to be, like ChatGPT or anything like this, enormous. So, what we care about, as with our algorithms hats on, is we care about how long it would take us to find this. Okay? So let's go through and let's do this briefly, this example right here. There's going to be a further example in the quiz in a second, but let's do this example. Yeah, question? So the gradient is going to be, you could think of the direction of greatest change. So it's a direction of greatest change, like with all directions. It would be if I were to take a very, very small step in this direction, I just change my variables dependent on these terms, very, very small. Like take these, multiply them by epsilon, and then add them to this, then that would increase the function as much as possible. That's one other way to think what the gradient is. But really, it's the same thing as a normal derivative. It is the slope. It's just multi-dimensional slope. Okay? Okay. I know a lot of people have trouble with when we move into multi-dimensional, when we move into beyond 1D or 2D. Don't worry too much about it. Try visualizing in 3D. That's probably the best way to do it. You can think of, like if I had it's a little bit hard to draw on a board, but if I had some surface like this. So like I have two variables, so I have some function of x and y, and then I have my y and my x. Then if I find some point, the gradient at that point with respect to x and y is going to be a direction upward, the direction most upward. What it really is it's a two-dimensional vector. It tells me how to change x and y to increase them as much as possible at a very, very small scale. Yes?
It's been a while since I took multivariate. Is the gradient parallel to the xy plane?
Yes, it is. Yes, it is. The worrying about that, by the way, that statement is true, but may not actually help you with understanding this. Technically, what it would be on the xy plane, and it would be centered at the origin. Not an important point here. The important point is what that direction means. That direction is how I should change my x and y to increase whatever function is arbitrarily much. In gradient descent, we do it the opposite way. We subtract it to move down as much as possible. That is, it helps us minimize the function. Let's not worry too much about that, though. All I want you to understand is what that thing is and why we might want to calculate it and the scale of that computation. Because when we talk about ChatGPT, we're talking about hundreds of billions of variables. So these gradient vectors are going to be enormous. They're not going to be 5, they're going to be 500 billion. Right? And we've been talking a lot of time in class about how we optimize computations. Particularly, we've been talking about dynamic programming. You can imagine that sort of speed up that we might see versus naive, going 2 to the n down to O of n would be very meaningful here. And in fact, this is how we're even able to do networks this large. If we didn't have some clever way to calculate these, and in fact a clever algorithmic way to calculate these for arbitrary networks, then we wouldn't be able to do what we do today. It's an essential piece of the puzzle as to how we got modern AI. So again, important algorithm, worth understanding, something that I would recommend that you implement on your own. And in fact, I've uploaded to Piazza a bonus problem where you can implement this from scratch for an arbitrary neural network. If you're able to do that project, that is classically homework 1 in my version of 389, but I probably won't be running 389 again for some time. So it's okay if you guys can do that one. So I gave it to you. I actually gave you a modified version of it, but it's on there, and there's 3 stars available. Okay? Cool. So let's look at the example. And again, if you have questions, ask them early on in this class. Okay? More so than other ones. Getting lost in the notation can really ruin the class for you. Okay. So let's just do an example real quick. So again, we'd like to find the gradient of this function with respect to x. Okay? So we already did the first one, so we knew that the partial of, or we did the 5th one, I suppose. The partial of y with respect to x5 was equal to this entire expression, x1, x2, because that is being multiplied by x5. That's fine. Plus x3, x4. How about the others? Partial y, partial x4. What's that going to be? Why don't you all take a second, solve them. This should take you just moments. It shouldn't take too long, okay? Yeah.
And literally yesterday, I was like,
So it is.
yeah.
So if you're going to pick a flight, so you're saying should it be wide? That is the actual.
Did you not take any?
So the graph is
He wants us to do like partial to x4, x3, x2. Find all the partials.
Okay, that makes more sense. Okay. So, if you had a little bit of trouble with this, by the way, and you are interested in machine learning, study up calculus. First recommendation there, good place to start. Otherwise, we still should be able to calculate these derivatives if we have a basic calculus understanding. You may be tripped up a little bit by the notation or anything like that, and in fact, got called on something here. To make it a little bit more clear what the gradient is, I relabeled these. I used y as one of the axes, so I want to make it very clear. The example, like relationship here, would be if we had x1 and x2, and then y is the height. Does that make sense? So just to make it a little bit more clear. Okay. So, what do we get for the derivatives? This one. Yep, so what I want to point out is that this is also a chance for us to use the chain rule. Do people know the chain rule? Okay, today we're going to be talking about algorithmically how to use the chain rule. The chain rule, for any of you who don't know, is 4 single-dimensional things, that is for scalars only. This is an important thing to know, but it only matters on the bonus in this class, but it's still an important thing to know that this rule is only true exactly the way I'm going to write it for one-dimensional things, for scalars, is that the partial derivative of, let's say, x with respect to y, or I'll do it the other way around, I'll do y with respect to x1, something like that. Y with respect to, let's say x4 actually, I'll use that exact example, is going to be equal to the partial of y to something else, which is a function of x4, times the derivative of that thing with respect to x4. Okay? So for example, we can say in here that a is equal to, sorry I'm drawing a little bit of a slant, a is equal to x1, x2, plus x3, x4, or yeah, like that. So say a is equal to this, and then I can do each of these derivatives together. So the first derivative, this would be a derivative of a, or y with respect to a. In this format, y would now be equal to a times x5. Okay? That makes sense? This is like U substitution if you've heard it before, but I don't use a particular name for it. We're doing chain rule. I guess I'm using that name, but we're doing chain rule. And we're deciding that this is going to be called a so that we can do our chain rule. And then this derivative of this with respect to a is very easily x5. So this is going to be, I'll write it here, this is going to be the derivative of y with respect to a, which is going to be x5. Then it's going to be times, as we start with there, the derivative of a with respect to x4, which as we saw before, is just going to be here, derivative with respect to x4, fairly easily to see that it is x3. Okay? Everyone happy with that? So the derivative is, as was said over here, x5 times x3. Okay, yes?
We're probably doing this for also distribute 5 over.
We could. The point, this is actually important. We are not going to be able to do that in general. I'm using multiplication because it's an easy function for you to take derivatives of. The example in the quiz, even, the one you're going to do there, you're going to see that you can't do something like that. Okay? So, any last questions on this? Yeah? Yes. That's what the gradient is equal to. Yeah. So, I guess maybe I'll write it over here just so that everyone can reference it. I think I do actually, do I have it on? Yeah, it's written on the quiz. So it's that nabla symbol, which is a downward triangle, is the gradient of whatever function is written next to it, in this case y, with respect to x, which is a vector in this case. Okay? And that's what that definition means. Alternative, yeah? We are going to be calculating gradients. So the backpropagation algorithm returns a gradient. So we're going to get some function like this, and then we need to return the gradient, not just a single derivative. And similarly to how we want to do some of our algorithms, like I want to, we're going to be able to do something clever to do that quicker than the naive approach. A naive approach would be going through here and individually calculating each one of these. And in fact, I'm going to point out something real quick. If I do the next one, does anyone notice anything about the next one? So derivative of y with respect to x3. x5, x4, In particular, if I write it using my chain rule, I can now write it as dy dA, or partial y partial a. I don't particularly care if you use d or if you use partial. Then times partial a partial x3. And when you notice, this, we already computed here. Gives you perhaps some idea of how we can do this optimization, is we can try to not repeat calculating these derivatives, these intermediate derivatives. Okay? That should give you enough of a hint, I think, to try the quiz. Also, my wife bakes a lot of bread these days, and today gave me a full loaf of bread. I gave the people who showed up earliest class today pieces of the bread. Who got some of it?
It's very good.
How was it?
It's really good.
Yeah, it was very good. Oh, you should have come early. I do also have a full slice of it. This is like the fancy one that she made, by the way. If anyone does the bonus today, you get the fancy bread. Okay? Or whoever gets the closest on the bonus, I'll even say. Okay? Yeah.
What kind of bread is this?
This is sourdough with some fancy cheese, some fancy pesto, and fancy sun-dried tomatoes. Yeah. It is pretty good. It's pretty good. I've tried it, by the way. Yeah. All right. Get going quietly first. Try it on your own first. I'll give you time to talk to people.
Every time I touch something.
We choose that. We can choose anything. It needs to be a function of the thing. So for example, in this case, like it needs to be a function of x4. So it's like, that's a function of x4. But it needs to be something, what we're going to end up doing with backpropogation is we're going to take every single operation and separate them out. So like I could call this like b plus c then, and then I can do that derivative and I can do the next derivative. So if I wanted to break it out more, I could, but I just decided on some place to break it out. Yeah?
What's up with x star?
So x star is bonus.
So
Or you should, no, you don't treat it like it's one, you treat it like a variable. Some variable that you're not calculating the derivative of. Yeah. You just don't need that derivative if you aren't doing the bonus. Yeah. So x star is only for bonus. You only need to calculate the derivative of x star if you're doing the bonus. You do need potentially to use x star for the other questions though.
oh,
And it handles product rule changing. Want to do it in as few operations as possible. Right after. Probably a little bit more fun to program. Lines of code. Yeah, so our really algorithm, if you choose, but it's not really algorithm, it's just write 4 lines of code that will
Each
calculate
one's element is calculated on line 1. Each element is calculated on line 1 of the code.
No, each one is calculated in one line.
Oh, in one line.
Oh, is it?
Yeah, it says on one line.
Okay.
I was real confused there. Alright, that makes sense. Because it's instead
Each
of like,
line is calculating one.
I thought it was all of them were
It's
supposed to be
still
done on
is.
line 1.
So, yeah, I think that is semantic misinterpretation, but I see. Yeah. On each of them, so each one is calculated on the corresponding opposite line. So A is I defined A as but A
Something with this structure using
you have to decide what
Because it's like as I'm like doing it out, trying to figure out what am I doing
I'm not using the chain. Let's look at calculating like x. Maybe that'll be good. Divide over dx. That's going to be
for any change
d.
this is an expression of
I'm not actually.
A is your I'm just not using it.
Are you a junior?
This is called y. Because we already said it's equal to y. I don't have that many. Whatever. I'll call this one Z. I'll call this W. And I'll call this.
So solve it in as few operations as possible.
But like, couldn't I do like?
So okay, so dy over dx2 is going to be dy over dz.
No, so you need to change it.
Oh, I'm trying to get us like keeping dy dx. That's like this
Okay, so there is something we can.
because like, if you use this whole, yeah, you're that line.
Second part's harder. I almost give second part as a bonus, actually. I think it's harder at least.
I don't think.
I mean, those are answers, but
It has to be.
I'm asking you to do the answer. I'm asking you to do the partial words. That's fine. Do this. That would be more possible. You don't have to do the thing. The bonus one too? Yeah. No, the bonus one was just to talk.
And then B is just this term right here.
It's just it's not really novel.
But the whole is like, so I guess we could talk about what so what is dy over dz?
Okay. So I'm gonna check in real quick. It seems like most people haven't finished yet. Don't worry too much about that. How are people feeling about this?
I'm confused.
Confused? What are you confused about?
I like what exactly.
Okay, that's fair enough. So for the first part, you can just solve the derivatives and do them line by line and just assign them. But you may end up repeating computation if you do that, if you don't like reduce things. And you'll notice then in the next problem, if you do this a little bit more cleverly, I suppose, if you notice the pattern of it, then the second part requires you to understand what's going on here and how to keep yourself from repeating computation. The second part is more of the real question, I would say. The first part is kind of like a warm-up and get you to understand how chain rule works and just checking in that that works. So as long as you're getting the gradient for the first problem, that's fine. I was asking you to do it like part by part, and maybe you noticed something about that, but if you didn't notice it, it's fine. You'll have to notice it for part 2. Okay, anyone else? Any other comments or questions? Okay. How do people feel about the calculus? Is the calculus tripping anyone up? For the star one, the star one is a tough one. For the calculus, again, this is I made a judgment call of how much calculus I should expect from you guys, and how much I'm willing to force upon you. This is sort of on the lower end, honestly. Calculus is something that, while it might feel like is not particularly important for computer scientists, you'll find out if you're interested in machine learning, it's important. If you're interested in electrical engineering, it's important. If you're interested in lots of different subfields, it is end up being very important. So it's worth a refresher. If you are you struggling with this, seriously, 3 Blue 1 Brown, excellent videos on calculus, linear algebra, and even deep learning, neural networks, and all that. It is actually, his videos are the ones that inspired me to get into machine learning back in the day. So I recommend them very highly. Yeah, my greatest claim to fame is I was in a Zoom call with him once. Genuinely. Okay. So continue. You can talk to partners now. I will allow you to talk to partners. Okay, well, let's continue.
Okay, so dy dz is 1, right?
Yeah.
Did you get the this is my thought, this is my little, like, the true
So we're using dy So I think the only way we can really save space is by like doing dy stuff like ourselves, and then just reusing that.
Yeah, we don't do dy dz.
The second part is about a piece.
We do it twice.
That's going to be dy dz times dvw times dwbv times dv, right? And then the idea is we're just going to like we calculate all these individually and we memorize them so that when we calculate the other variables, we already have the I don't know if that makes sense.
Why is that your rule? Oh, is that for x1 you do all that?
Technically, if you want to use the chain rule, right?
Well, wouldn't that just be this? Because you just. What
Oh,
if
you could do that too, by just adding like extra steps. Like
okay.
what you did was also right. But like I'm like doing it like every single little tiny thing, treating it as a chain rule step. I don't know.
It'll lead you to the, again, part 2 is where you have to actually use it. Part 1 you could just solve the calculus. Part 2 you have to actually do calculus.
You know, I just want to do There's something we have to memorize. See, when I took the class, we learned as normalize. So when he said,
Real
like,
quick.
oh, this is the most important.
So I say on the second part that there's an easy version of use division. That is not a recommendation. That's saying you can easily solve this with division. Don't use division. Yeah, that's what I'm saying. It's like nearly a one-liner if you use division. But without using division, you have to notice something. Yeah. Again, this is a stand-in for harder operations that I'm not doing because of the calculus background. Yeah. Can't do reciprocal. Reciprocation, you have to divide.
Okay. Yeah, no, that's the idea. But then, like, how do you do it as because they're tricky in some sense of these things. They're tricky in some sense, like, and be like, but obviously we only want to look at like some If we look at like contiguous, like if you look at like contiguous, like they're all mixed together. It's the same order. Like, let's think of like subarrays. Right? Yeah. And let's look at all the subarrays, including the leftmost side. Just store that information. That would take linear time to get all of those, and then we just do a run for each to get each like thing missing one bit. I'll explain that really well.
I see what you're saying. Yeah. You can start from the right, and then just like every element you add multiplying, add to like
It'd be linear space and complexity.
yeah, because you're not you just
No, you're not storing every single sub. You're only storing the ones that include the leftmost and include the rightmost.
What do you mean the leftmost and rightmost?
Like if I say like every time we look, what we have to notice is like we're multiplying everything except x2. We're multiplying these and these, right? So you can just store every single like product of things stretching from the left to some point, and every single product of something stretching from the right.
Oh, okay.
And we store them to easily cut. I don't know if that's really
are these two colors similar? What do you do? Right now, what is your name? Use that element
The problem I've realized is if I just had them switch, if I flip x3 and do one x star and if I swap those two terms, think of like x1 to the x star and x3 flip but I think
I know that seems tempted though. So good until it's so bad. What's that with the sauce?
People love it, but like I don't know, it's confused for me.
My internship this summer is in C++. I've never used C++. Am I not C? Am I child? Okay. Maybe I'll do the week online course.
Okay. So let's talk about answers here. And then I'm going to give you a little teaser of the backpropagation algorithm proper. Question for you all though. So now you've gotten a taste of what this is like. We have an option to either continue this next class and do it all the way out properly, or end it today and I'll say you guys can look it up now online and you can find this algorithm on your own. Who wants to know more about this algorithm? Okay. I will plan to cover the second half of this on Wednesday then. That said, we're still going to be talking about stuff, but I'm going to give you, at the end here, I'm going to give you a powerful tool that I'd recommend you think about and how you might be able to make an efficient algorithm using it. Okay, so this one, I've noticed that I've actually made it too easy, which is why people are saying, oh, I'm just going to do the calculus, I don't need to use any sort of efficiency. We'll see in the second one, there is a required efficiency, but also in general with these, I'll talk about something we can notice. So first thing first, I'm going to introduce a new tool that I find very helpful. This is how I end up doing my calculus if I ever get stuck on a derivative problem. This is how I tend to do it. Okay? So this concept we're going to call a computation graph. Okay? And that's going to allow us to calculate these derivatives. When we go and we talk about the backpropagation algorithm proper, we'll need a computation graph to understand this, but for now it's just a nice tool. Okay? And so the tool works. We're going to write out our entire computation as a graph, unsurprisingly. but we're going to write down every single operation we do. So we're going to start with the innermost, right? So the innermost operation is that we're doing this. That happens before everything else. This is sort of PEMDAS order, I suppose. So this is going to be the first thing we do. We're going to have x star. Wow, the marker just died on me. Okay. We're going to have x star. Let's make sure this one. Yeah. Okay, cool. X star and x1, and we're raising x1 to the power of x star. I'm just going to denote it like this. Okay? Make sense? You could flip these if you prefer that notation, but I'm just putting x star all the way on the end so we don't have to think about it. Okay? Then we take this, and I'm going to label it A. Okay? So I'm going to just label that first operation we do, capital A. Then we're going to do our next operation, which is multiplication by x2. Multiplying by x2. Then we have subtraction by x3. x3, right here. And then finally, we add x4. Okay? And I'm going to go through and label each one of these. So this is going to be x4. This is going to be then b. This one is going to be c. And this one is going to be y. Why? Because it's a total function. All right? Just to help us with this. Okay? So it's going to be y, because that represents, so here, this represents just this computation. So this would represent the value x1 to the power of x star. This one would represent the value after all of this computation before it. So this would be equal to x1 to the power of x star times x2. So these are very similar to the u substitution we might do, or the a value from the previous thing I talked about. Now, can anyone tell me anything that they might notice about if I wanted to take a derivative here? Let's say I want to take the derivative of y with respect to x2. Can we notice anything that I could do from this that would allow me to use chain rule in particular? Yeah.
You can essentially treat x1.
So we can do that, but if I want to find this derivative, I need to multiply multiple things together. It's not going to, that won't be enough. I could do that, and I, in fact, could call it A if I'd like to. But is there anything else I could do that would maybe give me the partial derivatives that I would need for a chain rule? So how could I know what chain I could do? Anyone? Yeah.
Is it just looking
Sort of. What we can do, and I don't blame any of you for not noticing this, what we can do is we can look at the path from y to x2. So if we look at if we find the path from for y to x2, we do our search, we know how to do that sort of thing. We can find here, here, here. Okay? And in fact, we can write down each one of these. So this partial derivative is going to be y with respect to c times c with respect to b, and b with respect to x2. Okay? So we can write each of one of these down. Say y with respect to c times c with respect to b times b with respect to x2. Okay? Does that make sense? Okay. Yes? So I'm finding a path from something to something. If I wanted a different derivative, if I wanted the derivative of c with respect to x1, I would find the path from c to x1. And in particular, by the way, in case anyone's wondering, if there are multiple paths, then you add them all together, and that then gives you the product rule as well. Okay? So this is a very powerful way to be able to calculate arbitrary derivatives. You'll almost always be able to break one of these problems down, and each one of these are very easy derivatives to do. So when you look at each one of these individual derivatives, you may be doing unnecessary work because some of these are very easy derivatives that you might notice that you can just get rid of, but we don't necessarily know that. So this is going to be our algorithm doesn't have a heuristic for if I know this derivative, just ignore it. So we need to come up with an algorithmic way to do this. Yes?
How could there be multiple?
For example, x e to the x.
Oh, okay.
Yeah. If you write out the computation graph for this, you'll notice that x diverges, and then you have to come back. So there's going to be multiple paths in the computation graph. It's not a tree. It's not a computation tree. It's a computation graph.
So we don't make
You could, but then you would just add all of the different paths. You can treat them as the same variable and add them together. Yeah. Okay, so what do we notice by this though? So if I want to calculate the derivative of x2, we've done that. How about now with x1? What would that chain be? Firstly, just try to do it on your own. I'm going to write it up here slowly. Okay. So what would the chain be? It would be this path. That's the path to it. That's pretty easy. We can go through each one of these terms. So it would be first dy dc, okay? Then times dc db, times db dA, and finally dA dx1, right? And what do we notice about this? We have to recompute these first two. So if I were to just compute these outright, or as many of you did, just write out the derivative using all of my terms, I will have repeated computation. So the secret that all of you missed on the first part of this, or at least however many of you missed, is the fact that we can write our derivatives as functions of other derivatives. So by doing this, we can actually save computation, right? And this is one of the big benefits of backpropagation, is this naturally happens if we are clever about it. So backpropagation essentially is dynamic programming for this specific problem, is how do we not repeat this computation? Okay, that makes sense? So you can find each one of these values. Big reason that people didn't notice this, by the way, these are 1. Those are all 1. So people didn't notice that it was repeated computation. And that's my bad, honestly, because you can just ignore them. You can very easily show that this would matter if you just put like a 2 here and like an 8 there. Then you can do that and you'd see that you do an extra multiplication each time. So I was a little bit sloppy with making it not a great example. At the cost of, I could have made it a better example, but then it would have been a little bit more complicated. Anyway. So hopefully you notice there that we have repeated computation here. The ideal solution to this, you don't repeat this computation. You use previous derivatives to give you your derivatives. And you'll notice if I made this chain very long, if I continued this chain off into infinity, then you'll notice that the amount of repeated computation grows, right? In fact, it would grow linearly with the amount of, or I guess exponentially with the length of this, because each variable would have additional variables that are additional repeated computation. Okay? That make sense? Okay. So now with that in mind, let's look at the second problem and try to make a computation graph for it. So the initial thing that we might want to do, for this I'm not going to check your derivatives, they're fairly straightforward ones. If you're not confident on them, please study up on your calculus. Cool, you can check with other people. But the second problem is a little bit more interesting. It tells us a little bit more about how an algorithm like this might work. How backpropagation might actually, what it might end up doing. Okay? So let's say that y equals x0, x1, wrong one again, x1, x2, etc. All multiplied together. Right? So first up, why do we need to do anything clever? So first thing that people noticed is if I just do derivative of y with respect to xn is equal to, or I shouldn't say xn, xi is equal to y divided by xi, that is correct. But in this case, by the way, because we're only allowing x0 through xn to be the input to this, we don't actually have y calculated yet. This would just be n computations and then 1 division. But we're banning division, so no division, right? In that case, how do I approach this problem? By the way, I can give a problem where you wouldn't have that easy of a solution other places, but then it would just make the whole function more complicated, and I don't want to do it. It would be like x0 to the power of x1 to the power of x2, something like that. You wouldn't have any other solution. You'd have to do it the clever way. Anyway, so with just multiplication, what do we notice about it? Well, first off, this is everything multiplied together except for that particular term. So this is going to be everything. I'll just do it as a product of xi's for I does not equal whatever the particular value. I'll say j, and then I'll say I is the thing I'm going to remove. So j does not equal I, and this is xj. So I just multiply everything together. Okay? If I were to do this naively then, each one of these terms, I would need to compute this, which would take me n time, because n different variables multiplied together, or n multiplications, I should say. And then I'd have to do that n times, so that'd be n squared. N squared would be the naive thing, but there's probably some repeated computation. I mean, in particular, if I just look at the derivative with respect to, let's say, x1, right, this is going to be, or I guess, yeah, x0 times the x2, yada, 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 right, this whole block of them. Right, I guess I won't put them in parentheses, I'll make it maybe less clear. So x0 times all of this, right, x2 and so on. And then we'd have something like the derivative with respect to x2, right? You'd have x0, x1, multiplied by, and then there's x3 and so on, right? And clearly there is some repeated computation going on there. I'm doing some multiplications that I could perhaps reuse. But how could we do that? Well, first, let's start by looking at a computation graph, okay? So let's move on from this, and I'll erase this also. If you need to know what a gradient is, you can watch my YouTube video on it, or you can look it up online. It's pretty straightforward. So I think I just swapped to the bad one again. So how could we draw a computation graph for this? Yeah. Yeah, so I'll go with the dumb thing first, and then I'll go with what you said. So let's go with the dumb one, which is I could just have x0, x1, all of these variables, xn, all just multiplied together, right? I could just say, oh, I have some multiplication that takes in all of these things together, and that doesn't save me anything. If I want to take the derivative, then if I were to calculate each one of these, I would just be calculating the whole thing again. But you notice a little bit of ability for us to make this more efficient if we realize that this is equivalent to if I put parentheses around each term, right? Just each multiplication is an individual operation, and I'm just going to repeatedly chain those together. So then my computation graph looks something like this. x0 times x1 multiplied together, and I'll call that A here. I'll call it output 1, just to make it maybe a little bit more easy for us to talk about this at scale. Then we're going to do the same for the next variable, x2, going to be O2, and so on, all the way down to On, okay, which is going to be y. So, or On minus 1, which is going to be y. So then if we want to do our derivatives, how might we do that? So we can start with one of these. If I take the derivative of this with respect to, so derivative of y with respect to some xi, what's the chain going to be? Yeah? Exactly. Yeah, so exactly. You're going to have some large chain of them. We're going to have some product of all of them. I'll use the product notation again. If you don't like product notation, just remember I'm just writing it as if it's a whole bunch of multiplications. Product of all of the derivatives starting at, so it'll be, I guess I'll start with the first one, which is dy d, just because it doesn't follow the same notation, dy do n minus 1, and then it's going to, or n minus 2, sorry. I'll call it O of n, then this goes up to n plus 2, okay? If you can ignore my off by 1 there, just so I have a cleaner notation over here. This is just going to be the n1. I'll explicitly write here that this is going to be O of n, and then it'll be xn plus 1. It's going to be, or xn n, and then there's going to be an xn plus 1 that gives us y. Sorry. That y, and then it'll be multiplied by xn plus 1. I'm just handling the off by 1, by the way. I'm not fundamentally changing the problem, just for notation. This then is going to go all the way from n to I, n minus 1 to I, and it's going to be then multiplying all the partial derivatives of O, I, or O-N, sorry. I guess I should say this is J equals every value from n to j. That's a short notation for like a for loop or something, where I'm multiplying every term. The derivative of that, this with respect to this minus 1. So I'm just going up the chain, multiplying all these things, and then doing it. Right? If I were to write it this way, it maybe becomes a little bit clearer that I am repeating computation. Same as before. If I were to compute these directly, I would be repeating computation. So in fact, what I can do is I can store these intermediate values, right? So in particular, what I could do is instead of writing this whole gross notation, which hopefully you still understand, it is important to understand what I'm saying here, but what I can do instead is just say that this is going to be the derivative of y with respect to x, respect to o I plus 1. Okay, so that's all the way to the term, or I guess it's just plus to I, right? O of I, right? So whatever term it is, and then all it needs to do is be multiplied by the corresponding thing, right? And what is that corresponding thing? Not quite. So again, we go through the chains. It's up this chain, and then the final step of my thing here is dO2 with respect to x, or OI with respect to xi. What would that derivative be? Yeah. So it would be that, but there's also a figure back. So it would be that. So I'll say that. Then the derivative of OI with respect to xi, right? And because of the structure of the problem, we know that this is in fact going to just be OI minus 1. But because we're multiplying, so OI equals xi multiplied by the previous term, right? Okay. So yes. So the way to understand these partial derivatives, one way to understand them, is you can say that any of these functions, when I'm taking this partial derivative, I can write this function as a function of the thing beneath it. So I can say, if I want to understand like OI, right, in that derivative, and say OI is equal to what? OI is equal to OI minus 1, right? So it's whatever I previously computed, whatever I previously multiplied, then multiplied by one new term, right? And that new term is going to be xi, right? Does that make sense? Yeah, so I'm taking the derivative of that to get the second term. And this first term is just capturing the entire chain that goes from y all the way up to this point, right? And it turns out that that's going to be a lot of shared computation for each one of these x's. I'm going to share a lot of overlap with those other chains. That makes sense? So by doing this systematically, what I can do is I can just do essentially a for loop where I go through and I calculate just one step, and then I calculate the corresponding x. Then one more step, calculate the corresponding x, and so on, so on, so on. So if I were to actually write this out here, right, what I could say is that the derivative of y with respect to any xi, right? So I'll say it like this. How about this instead? So first off, I'll say that the derivative of y with respect to on, just so I can get into my notation, is going to be what? Again, think of this as a function of this. What is it? Each one of these are multiplied together. Remember what the computation graph is trying to represent. Yeah? So I'm asking what the partial of y with respect to on is. So it's not going to be multiple partials because it's just one step, right? It's just a single step. So I'm not going to multiply things together. It's just going to be a single derivative. Yeah? It's going to be xn plus 1. So remember, y is going to be on times xn plus 1. So the derivative here is just xn plus 1. This is just to get into my notation, by the way. Then I can do a for loop. So then what I can do is I have a for loop where I say the following. So I'll say this is also going to, I'll rename this to derivative, I guess. I'll call this a cumulative derivative. cumulative derivative is going to be equal to this also. I'm going to use that variable name. And I'm going to do a for loop from n to 0. And in that loop, I can calculate for each step just one of these. So what I can do is I can then take that the partial derivative of y with respect to any of these x, I'll say I equals this, sorry. For any of these xi's, what can I do? So this is now where we can use the insight that we saw before. How can we use chain rule? So we previously have this computed, right? What can we do? Yeah. Yeah, so we're going to, so again, we look at the chain, right? So we have this one so far. Then the first thing I'm going to be computing is respect to xn, right? So it's going to be this partial that I've already calculated. So it's going to be, in this case, it's going to be partial of y with respect to on, or oi, sorry, because we're looping over I, right? And then, what do? So then, we take the derivative with respect to this, which is multiplying it by what? So the other derivative that I need here is pretty clearly, by chain rule, is going to be the partial of oi with respect to xi, right? And what's that value? On minus 1. So we saw that before. That's each on is just the previous one multiplied by its corresponding x. Okay? So this is going to be the thing, meaning this, I can just use on minus 1. We'll talk about that in a second. And then we need to update the next one of these, because we're going to be looping over each one of these. So we need the next one of these. So dy do I minus 1 is going to be equal to what? Let people figure it out, I guess. Okay. Anyone want to tell me? Again, if you're getting stuck on this, it's not because you don't have the ability to do the problem. You probably don't understand the problem. It's more of a notational or language barrier in some way. I promise this is a reasonably phrased problem that I'm giving you, but you probably don't have as much calc exposure as could be beneficial to you. I'd recommend, again, if these problems are difficult for you to think about, difficult to reason out, probably means that you need some stronger background in calc. Yeah?
XI?
It's going to be xi, exactly. So it's going to be not just xi. Yeah?
XI minus 1.
So, also not the exact answer. It's going to be this previous partial times that, right? Because we have the entire chain up to it. I can't say that the chain from, y all the way up to oi is just x1. Instead, it's going to be the chain up to here and that extra step, right? Make sense? Yeah. So it's going to be dy, oh man, the marker's dying again. dy doi, then multiplied by, is it xi or xi minus 1? It is going to be xi plus 1, isn't it? Right, this derivative there is going to be it's going to be xi plus 1. I plus 1. Okay. You can work that out if you like. Okay. So, oh no, this it's just xi. Sorry. It's minus 1. It's minus 1. I thought we were calculating this. Yeah. So it's xi. Sorry. Because we have that oi is equal to oi minus 1 times xi. You can see it in the computation graph. Okay. So, this is all well and good. So we now have a for loop to calculate these derivatives. Is there any problem with this? Yeah. So that's not the end of the world. We have it saved in memory. So we're not recalculating that derivative. We just have it saved in memory. So that's not an issue. It's not an issue. There is an issue, though. There's a pretty big issue. See if you notice it. So I care about doing all of my computation quickly. Is there anything that might be slow about what I'm doing? Let's look at each of the terms. So this I've previously calculated. That's totally fine. Xi, that's already in memory. That's totally fine. OI minus 1. How am I getting that? Yeah? So the way I've described it so far, I would have to recalculate each one of them. Calculating ON is doing all the calculation of ON minus 1 and then doing one more computation. So clearly that's a ton of repeated computation. So, in fact, in the backpropagation algorithm, this is going to be my first real mention of it. In the backpropagation algorithm, what we do is we actually do a forward pass first. So this is a backwards pass. As we go backwards and we calculate each one of our derivatives as we go. But first, we're going to calculate a forward pass where we go through and we calculate each of these intermittent values and store them in memory. Okay? So what we're going to do is we're first going to do our calculation. That is, we're going to do another for loop where we go forward, where we say, where we're trying to calculate these values, these ONs, OIs, I'll say. So we do a forward pass, we do a single forward loop, going through, saving each one of them, and then we can do our backwards pass and do each one of these. So if I do this, what's the runtime of each? So what's the runtime of doing the forward pass? O of n. I'm doing just n, and my loop is only n long, and each one I just do a single multiplication inside of it. Okay? Secondly, if I do my backward step, my backpropagation step, then how long does that take? How many multiplications am I doing? So I'm doing O of n, or more properly, I'm doing 2n. I'm doing 2n because each one of them I'm doing 2 multiplications. That's okay. That means that this entire algorithm will end up being O of n. Okay? Now, some of you might have noticed, I heard Thomas saying this, that what we can just do, we can just, store all of the subsets that start on the left, all the subsets that start on the right, that sort of solution, and then do multiplications of each pairing of them. That will, in fact, or not each pairing of them, each corresponding pairing of them. That is exactly the same as this solution. Okay, if you heard that solution or you thought of that solution, they're exactly the same. In fact, what we'll find is that this backpropagation algorithm is very likely to give us the optimal way of storing our memory to calculate our derivatives. There is some improvements we can make over backpropagation algorithm. Maybe we'll talk about them a little bit more next class. But overall, we'll end up doing as little repeated computation as we need to in general. So, yeah.
I don't know if this is going to be addressed, but why don't we just do division?
So in real life, we wouldn't have this problem. That's the reason. So in real life, we'll get a much more complicated problem, and this will still work. If you'd like to see what the real computation that's used for backpropagation, the actual use case, flip over the sheet and look at the bonus. If you can find a faster way to do that derivative than what I've explained here, then talk to me after class. That would be a big deal if you can find a much faster computation than that. You'll see that doing this is going to give you an optimal sort of computation. Okay? All right. I think with that, any questions on backpropagation? If you're interested in this, 3 Blue 1 Brown has excellent videos on it. The quiz, by the way, is not on Gradescope yet. I'll add it soon.